So we've seen this slide before that says heat is the transfer of thermal energy, that's the definition of heat, between two bodies at different temperatures. We said temperature and thermal energy are not the same thing. Heat and temperature are not the same thing. How do they relate? Well, that's what we're getting started on today. One way that they relate is through specific heat. Specific heat is the amount of energy it takes to raise the temperature of 1 gram of whatever substance by 1 degree Celsius. And specific heat has these units of joules per gram degree Celsius. So the specific heat of water is something that we will talk about quite a bit, 4.18 joules per gram degree Celsius. It takes 4.18 joules to raise 1 gram of water by 1 degree Celsius. That's the specific heat of water. Heat capacity takes specific heat one step further and says it's how much heat is required to raise any given amount by 1 degree Celsius. So heat capacity is joules per degree Celsius only, because heat capacity can be thought of as the mass of some substance times the specific heat. So if you have 100 grams of water, multiply it by its specific heat, that's a 1/8. The heat capacity of 100 grams of water is 418 joules per degree Celsius. It takes joules per degree Celsius. It takes 418 joules to raise 100 grams of water by 1 degree Celsius. If it were 1,000 grams, put another 0 on the end of that. The capacity is determined by the amount of substance you have. The specific heat is not. And we've actually used some terminology before that says if it is intensive, that means it is independent of the amount of substance you have. Specific heat is independent of the amount of substance. You can look up tables and tables and tables of specific heat values, but you cannot look up tables and tables of heat capacities because it all depends on how much you have as to what the heat capacity actually is. So if we find in some experiment in the lab that 700.5 joules of energy was needed to increase the temperature of 362 grams of gold from 25 to 40, what's the specific heat of gold? Well, we've already talked about the specific heat units are joules per gram degree Celsius. Well, we can just plug in the values that we've been given, except we've been given 2 temperatures. How do we find what temperatures to put in? It's how much the temperature is changing. So delta T, delta always means final minus initial. So our delta T is 40 minus 25. That's 15 degrees Celsius that this thing is changing by. So 705 joules of energy divided by 362 grams multiplied by 15 degrees Celsius. Do that little math there and you get the specific heat of gold, which actually is matching this table here, 0.129, 0.13 if you do that math. The way that those values got in the table in the first place is through experiments such as these to measure the specific heat. It does not matter that it was 362 grams. If it were more grams, this joules would have been more and the Celsius would have been more. If it were fewer grams, this joules would have been less, this Celsius would have been less. You do all these experiments so that you can get these tables of specific heat data. See, here's the specific heat of water that we've already mentioned, 4.18, 4.184 joules per gram degree Celsius. Yep, we'll use that one several times. So the way a lot of these experiments are done to measure the specific heat and to measure heat of reactions and delta H's of reactions is through something called a calorimeter. This thing is a calorimeter. We won't have the luxury of doing this in person, but we're going to do some calorimetry experiments and calculations digitally anyway. So a coffee cup calorimeter is what this thing is. It's a constant pressure calorimetry. As you may recall, delta H is a constant pressure process, so this has to be a constant pressure calorimeter if we're going to compare and measure delta H values using these. So we take advantage of the relationship that Q of the system is equal and opposite. Q of the system is equal and opposite to Q of the surroundings. Well, we saw that previously, that if the reaction is exothermic, Actually, let me change this to say Q of the reaction. Q of the reaction is equal and opposite to Q of the surroundings. So if the reaction is exothermic, that means Q of the reaction is negative. So put in a double negative, and the Q of the surroundings has to be positive. This is a very important principle in calorimetry. Whatever heat is gained or lost by the reaction is the opposite by the calorimeter. So if the reaction is exothermic, the calorimeter will absorb that heat, and the absorbance of that heat causes the thermometer temperature to actually increase, because the thermometer is part of our surroundings. We actually answered that in a previous chem activity question. So this is super important, and the signs in calorimetry can be very difficult. If the temperature goes up, it's because the thermometer is absorbing energy. If the thermometer is absorbing, it's because the reaction is releasing, and vice versa. Okay, a couple of things we need to know about calorimetry. We need to know the heat capacity of our calorimeter. How much can the coffee cup itself absorb? How much can the stirrer absorb? How much can the thermometer absorb? How much heat can these items absorb? Because we want to know specifically how much our reaction is letting off. So the heat capacity of the calorimeter is all the container components that we just discussed, plus the stuff that's actually inside the calorimeter. A lot of times we will have water in there as our basic thing that absorbs the heat or releases the heat. The heat capacity of the solution is usually much larger. It's true. There's usually a lot of water, and the calorimeter itself, the container itself, doesn't usually absorb a lot. We use these calorimetry experiments to measure H and Q. H and Q are not the same thing, but they are proportional. H has the value, usually, of kilojoules per mole. Sure, we might see it in joules per mole sometimes, but kilojoules per mole is usually what it's in. And Q has the units of joules most of the time. So how do these two relate? Q divided by moles of the reaction would equal delta H of the reaction. Delta H of the reaction is equal to Q of the reaction divided by the moles of the reaction. You want to see how that works in practice? Let's do it. 61 milliliters of this and this. 61 milliliters of this was combined with 61 milliliters of that in a coffee cup calorimeter, just like that last picture. The initial temperature of both solutions was this. The temperature of the reaction was that. How many kilojoules are given off per mole of HCl? Assume some stuff. Yep. Where do we go? I'm adding NaOH and HCl. This is a throwback to Chapter 4, and back in Chapter 4, we saw acid-base reactions make salt plus water. This is an acid-base neutralization reaction. Acid-base neutralizations are often, one type of reaction. They give off or absorb heat. I'm not going to say anything more. So there's that reaction. It reacts in a 1-to-1 mole ratio like this. We're adding 61 milliliters of 0.56 molar NaOH and equal amounts of HCl. So what that actually tells me, if I throw it all the way back to Chapter 3, there's no limiting reactant. These are going to react completely. They both run out at the same time. So that's relevant for something we'll do in a moment. But the initial temperature was 24. The temperature after reaction is 27.7. The reaction temperature went up. And because the reaction temperature went up, that tells me this reaction is exothermic. Because the temperature went up, it went up because the thermometer absorbed heat. The thermometer absorbed heat that the reaction was giving off. That's the biggest point in all of this, that you've got to get the signs right in all this calorimetry stuff. So, if we start by trying to determine the C of the calorimeter, the heat capacity of the calorimeter, we're told the cup, the container, is 21 joules per degree Celsius, but you have to add in the heat capacity of the water. Whatever contents you have in there, and we're adding 61 milliliters plus 61 milliliters That's 122 milliliters. 122 milliliters times our density, 1 gram per 1 milliliter. 122 grams of water is being created. Water is our product up there. So 122 grams of water times the heat capacity, times the specific heat of water will tell me the heat capacity of my water. So do that little math, multiplying those two, adding in that, we get 530.96 joules per degree Celsius. That is the heat capacity of my calorimeter. Heat capacity of my calorimeter. However, I'm being asked to answer how many kilojoules are given off per mole of HCl. Why did I go all the way down this path talking about the heat capacity of the calorimeter? Because I'm going to get there. Because I'm going to get to what they're asking by finding the heat capacity of the calorimeter first. So a couple more formulas that we need to know. Let me erase all this stuff. Q, the heat in a reaction, has two basic formulas. Q equals MS delta T and Q equals C delta T. The reason those are the same formula is because M times S is C. The heat capacity is the mass times the specific heat. So that and that are the same dang thing. But the heat given off by the reaction or absorbed by the calorimeter can be calculated through one of these equations. Because we just found the heat capacity of the calorimeter, let's find it using that equation. The heat capacity of the calorimeter we found was 530.96 joules per degree Celsius. And my delta T is 27.7 minus 24. That actual math gives me 1964.55 joules. And I left some space here to say, what's that the Q of? Because this temperature is going up, this is final minus initial, this is the Q of my calorimeter. And Q of my calorimeter is equal and opposite of Q of my reaction. So Q of my reaction is negative 1964.55 joules. Because my reaction is exothermic. Don't know where that S came from. Exothermic. So does that help me answer this question? How many kilojoules are given off per mole? It's getting me closer, but I'm still not there. I'm told how many joules are given off in this reaction, but that is not an intensive property yet. This specific number right here is specific to this combination of reagents. I want to find a number that's universal for this kind of reaction. Oh, I erased the reaction. For sodium hydroxide being added to HCl. So in order to find something universal, that means I need to find delta H. And delta H is Q divided by moles. So Q divided by moles. So I'm going to start with negative 1964.55 joules. I actually want it in kilojoules, so I'll convert that in a moment. And then moles of the reaction. How many moles of this reaction are there? Well, there's 0.061 liters of sodium hydroxide being added, and it's 0.56 molar. We can't forget that molar means moles per 1 liter of sodium hydroxide. Multiply those, and I get 0.034 moles of sodium hydroxide, moles of reaction that are happening. So I divide that in 0.034 moles, do my little mathy math, and I get delta H of the reaction is equal to negative 5,700 joules per mole. But it said kilojoules per mole, so 57,000 turns into 57.8 kilojoules per mole. The end. The hardest part about calorimetry is determining whether you're finding Q of the reaction or Q of the calorimeter and knowing that they are equal and opposite. From there, it's just formulas and figure it out. We can do this. Let's do this.